Hello everyone, welcome to lecture number 24 in physical organic chemistry. In our previous class we had started off with cycloaddition reactions, their theory and examples, and we had seen the 2pi plus 2pi thermal and photochemical reactions. We had also seen the 4pi plus 4pi photochemical cycloadditions. Today we are going to discuss a very important aspect of cycloadditions, that is the 4pi plus 2pi Diels Alder Cycloadditions. As always, most of the material in this particular lecture has been sourced from Professor Shankar Raman's Pericyclic Reactions textbook and his lecture notes. The Diels Alder reaction is essentially named after Otto Diels and Kurt Alder, who were the discoverers of this particular transformation in 1928. Essentially, this is a thermal cycloaddition between a cisoid conjugated diene and a dienophile. The dienophile usually is an olefin or an acetylene. Now it can be represented in the most general way as it is shown here. A six-membered ring is formed by a concerted transformation, which is a 4pi s plus 2pi s, and the reaction essentially is highly regioselective and stereoselective. So you can see here, depending on what you use, either a olefin or an acetylene, you can get either a cyclohexene or a cyclohexadiene molecule. The reaction, as we mentioned here, is highly regio and stereoselective transformation. Let us see how this is going to be regio and stereoselective. Apart from carbon-based dienes and dienophiles, you can also use heteroatom substituted dienes and dienophiles. Okay, so any of these A, B, C, D, E, F or X, Y can also be a heteroatom. Therefore, not only is this reaction very useful for the synthesis of cyclohexenes and cyclohexadienes, but they are very useful for the synthesis of six-membered heterocyclic ring systems. Now, as you can see here in this particular transformation, if you are going to react a diene and a dienophile with four different groups, then you are going to generate four different contiguous stereocenters. So this reaction is going to generate this cycloadduct bearing four new asymmetric centers. This is the best part about Diels Alder reaction, and this particular aspect of Diels Alder reaction has been utilized extensively in the synthesis of natural products. We had seen earlier in the previous class the frontier orbital method of analysis for 4pi plus 2pi cycloaddition reactions. So we had seen in a 4pi s plus 2pi s cycloaddition, the interaction of the frontier molecular orbitals have the same symmetry when they are interacting. Therefore, results in a bonding overlap in the transition state. Therefore, the 4pi s plus 2pi s cycloaddition is thermally symmetry allowed. On the other hand, the 4pi s plus 2pi s has an antibonding overlap in the transition state and therefore is symmetry forbidden and subsequently disallowed. We had also seen in our previous class the orbital correlation method for the 4pi s plus 2pi s cycloaddition, and we had seen that there is a plane of symmetry that is maintained throughout the process, that is the sigma plane, And the symmetry properties of the molecular orbitals in the ground state correlated with each other, and therefore the 4 pi s plus 2 pi s was found to be thermally symmetry allowed. So there was no crossing of the non-bonded label, and the symmetry properties in the ground state correlated with each other. We also saw the Diels Alder model for 4 plus 2 cycloadditions, where we saw that this is a Huckel type aromatic transition state and therefore is thermally allowed and photochemically forbidden reaction. And according to the Woodward-Hoffmann generalized orbital symmetry rule, we saw that the superfacial overlap had one component in the 4q plus 2 suprafacial and 0 components in the 4r anterofacial. Therefore, the total was an odd number, and therefore this was allowed in the ground state. The opposite, the anterofacial approach was also allowed in the ground state. But obviously, this is difficult to achieve geometrically. And the other two options, the anterofacial suprafacial and the reverse suprafacial anterofacial, were obviously thermally not allowed because these had a total of even components in the ground state. Therefore, according to the Woodward-Hoffmann generalized orbital symmetry rules, these would not be allowed. Let's look at the Diene portion for a Diels Alder reaction. A variety of conjugated dienes can be used in the Diels Alder reaction. The basic requirement is that the diene must have a cis conformation. If the diene cannot have a cis conformation, then it cannot take part in the Diels Alder reaction. Obviously, because the two ends of the diene are too far apart to overlap simultaneously with the dienophile. So any of the dienes that are part of a rigid transitoid structure cannot take part in a Diels Alder reaction. For example, you can see in this particular example, as well as in the second one and the third one, they are all transitoid structures and they are rigid. They are part of a ring system. Therefore, they cannot turn into the S-cis form. Therefore, they cannot react under Diels Alder conditions. Another type of diene which bear extremely bulky substituents. These will destabilize the cis form because there is a severe steric strain, and therefore these also do not exist in the cis form. Therefore, these are also unreactive in the Diels Alder reaction. Compared to acyclic dienes, cyclic conjugated dienes are very reactive because the two ends are held together by a tether. However, as you go to higher and higher spacers, the reactivity of the diene starts to fall. With increasing ring size, what happens is that the distance between the C1 and C4 of the diene increases. That is, the distance between the terminal carbons increases, and therefore the overlap in the transition state becomes quite ineffective, and because of which the reactivity decreases. Because if you look at these dienes, essentially they have to overlap simultaneously in a pericyclic fashion with the orbitals of a dienophile, which is a fixed distance. Therefore, if you have a very large distance between C1 and C4, it finds it very difficult to have an effective overlap with the orbitals of the dienophile. Therefore, the reaction becomes ineffective as your distance between the terminal carbon grows, and therefore reactivity goes down. So the highest reactivity is observed for cyclopentadiene, which dimerizes very readily even at room temperature in a 4+2 cycloaddition reaction. Let's look at the dienophile now. The dienophile is usually an alkene or acetylene, as we had mentioned earlier, but more importantly, it is an alkene or acetylene bearing an electron withdrawing functional group. This is a normal Diels Alder reaction. In the normal Diels Alder reaction, the reactivity of this dienophile will increase with increasing electron deficiency of the double or triple bond. What happens because of that? Because of that, the lowering of the LUMO takes place for the dienophile. Which substituents can you put on the dienophile? You can put a variety of substituents. You can put carbonyls, esters, cyanides, nitro, sulfones, variety of substituents you can put. Another class of dienophiles are cyclopropenes. These are extremely reactive. Why are they very reactive? Is because of their very high angle strain of the double bond. When you employ this in a Diels Alder reaction, this gets now converted to a single bond, thereby releasing some of the ring strain. Same is true for benzynes, and these benzynes are also extremely reactive as a dienophile. Let's look at the rates for Diels Alder reaction and the factors that affect the rate of a Diels Alder transformation. The most important interaction in a Diels Alder reaction is the homo-LUMO interaction between the diene and the dienophile. In a normal electron demand Diels Alder reaction, that means a dienophile that has an electron withdrawing group on the dienophile. The interaction of the HOMO of the diene and LUMO of the dienophile is the dominant interaction. Whereas when you change the electron demand, that is an inverse electron demand Diels Alder reaction, you will consider the LUMO of the diene and the HOMO of the dienophile. If you can see this particular figure, you see here we are going to see the orbital overlaps between, this is maleic anhydride, okay, the HOMO of the anhydride is drawn here, whereas the LUMO is drawn here, and the pi system or the molecular orbitals for the diene are drawn here. This is with butadiene. So according to the frontier orbital overlap, we have to consider the HOMO of the diene and the LUMO of the anhydride, or you have to consider the LUMO of the diene and the HOMO of the anhydride. As you can see here, the energy gap between the HOMO of the diene and the LUMO of the anhydride is much smaller than the energy gap between the HOMO of the anhydride and the LUMO of the diene. So this is the best overlap to be considered for a normal electron demand Diels Alder reaction. As you can see here in this particular diene, if you start off with butadiene and simple ethylene, you can see that the gaps are more or less comparable. So this gap is more or less comparable to this gap. Therefore, this particular transformation is not very efficient. Normally, this transformation needs very high temperature and pressure to form a cycloadduct. Whereas if you go to the normal electron demand Diels Alder reaction, you find here, as we had seen previously also, that this particular interaction is the lowest energy gap interaction and has a better overlap between the orbitals. In the second case, this overlap between the LUMO and the HOMO of the dienophile is not a very effective overlap because of the large gap between them. In an inverse electron demand Diels Alder reaction, the HOMO, excuse me, the HOMO of the dienophile is raised because you have now an electron donating group on it. Whereas the LUMO of the dienophile remains more or less the same, or if it has an electron withdrawing group, then the LUMO is also brought down in energy. Therefore, now this particular energy gap becomes the dominant interaction. This is for the inverse electron demand Diels Alder reaction. What do we mean by this? We mean that the structural and electronic factors which lower the magnitude of the appropriate HOMO-LUMO separation will accelerate the Diels Alder reaction. The substitution of diene and dienophile with functional groups that cause strong electronic perturbation of the pi system, or by catalysis by Lewis acids, these are common methods to accelerate the Diels Alder reaction. The choice of the substituent must be complementary on the diene and dienophile. You cannot have both electron withdrawing groups or both electron donating groups. Either one of them have to be electron withdrawing and the other has to be electron donating. Preferably, the diene has to be electron rich and the dienophile must be electron poor. Like I mentioned, for a normal electron demand Diels Alder reaction, the diene will bear an electron donating group which will raise the HOMO as well as the LUMO of the diene with respect to the unsubstituted diene. So if you see here, if we put an electron donating group here, okay, if we put an electron donating group, then the HOMO of this diene will be raised. If on this dienophile we put an electron donating group, then again the HOMO will be raised. Whereas if we put an electron withdrawing group on the dienophile, the HOMO and LUMO both are lowered. So the dienophile bears an electron withdrawing group in the normal electron demand Diels Alder reaction, which lowers the HOMO as well as the LUMO of the dienophile with respect to the unsubstituted dienophile. Therefore, the HOMO of the diene and LUMO of the dienophile is the lowest HOMO-LUMO separation. So this explains why dienophiles such as maleic anhydride and tetracyanoethylene are so highly reactive in Diels Alder reactions, especially with butadiene when compared to ethylene. Suppose you see the transformations of 1-alkoxy and 2-alkoxybutadiene. These are found to be much more reactive than butadiene themselves. For example, if you see OR at the 2 position, or you see these kind of dienes, then these are far more reactive than butadiene themselves. Obviously, because the HOMO has been raised. So you can see here from this particular diagram, if we are seeing a dienophile, okay, in this particular case, if you start off comparing with ethylene, when you put an electron withdrawing group, what happens to the lobes? See here, when you start off with ethylene, both the coefficients are almost equal. Whereas if you have an electron withdrawing group on the dienophile, then the largest coefficient or the largest orbital coefficient is at this particular position, and there is a lowering of the LUMO. Whereas if you have an electron donating group, obviously the HOMO is raised and the largest coefficient again now becomes on the terminal carbon. If you consider the dienophile, simple butadiene has an coefficient distribution of this kind in the HOMO and LUMO. If you put an electron withdrawing group at the 2 position for butadiene, then the most important orbital, that is this one, will have a large coefficient. If you have electron withdrawing groups, obviously you will have to consider the LUMO and not the HOMO. Whereas if you have electron donating groups, then the largest coefficient becomes at this terminal carbon, and the HOMO is also increased, the LUMO is also increased compared to the starting material. Okay. So in the inverse electron demand, we already saw, in the inverse electron demand, you will have an electron donating group here and you will have an electron withdrawing group here. In that particular case, you will consider the interaction between this orbital and this particular orbital. So the LUMO of the diene and the HOMO of the dienophile is the lowest energy separation of the frontier orbitals for the inverse electron demand Diels Alder reaction. What is the cis rule for Diels Alder reaction? Now the effect of the supra-supra overlap in the Diels Alder reaction has a bearing on the stereochemistry of the product that is formed. This is known as the cis rule. This cis rule was formulated by Alder and Stein in 1937. According to this rule, the relative stereochemistry of the substituents in the 1,4 positions of the diene and the 1,2 positions of the dienophile is retained in the adduct. Obviously, why is this? This is because of the supra-supra interaction between the diene and dienophile in the transition state of the reaction. Therefore, if it is a trans 1,4 disubstituted diene, for example this particular diene, then the 1,4 substituents are cis with respect to each other. Okay, so you can see here these are now cis with respect to each other in the cycloadduct. Whereas if there is a cis trans 1,4 disubstituted isomer, then you would have 1,4 substituents which are trans. For example, you see here and here. These are trans to each other. Therefore, the products you would get, these are trans to each other, because the relative relationship in the starting material was one was trans, one was cis. You may ask why we are not considering both of them as cis. You already know that if the diene has 2 cis substituents on it at the terminal carbons, then there is a severe steric interaction between them and the diene is not that reactive in the Diels Alder reaction. What about the dienophile? What about the stereochemistry of the dienophile? If the dienophile is trans, then in the adduct, the two substituents will remain trans. If the two substituents are cis in the dienophile, then in the cycloadduct, they will remain cis. For example, you can see here, these two have a relative stereochemistry of Z, whereas here, these two have the E stereochemistry. So you can see in the product, in both the cases, the stereochemistry is retained, whether it is a monocyclic or a bicyclic cycloadduct. You can generalize this in this particular diagram. You see here, depending on the relative stereochemistry of A and B, you will have the relative stereochemistry in the product. Similarly, if you have a relative stereochemistry between the groups on the dienophile, then those will be also translated in the product. There is something very important called as the Endo rule. This was formulated by Alder. It says, for example, let us see a couple of transformations. You can see here that you can form two products depending on the orientation of the diene and dienophile with respect to each other in the transition state. These products are called endo and exo. You can look at this particular transformation where cyclopentadiene is reacting with maleic anhydride to give you two cycloadducts. One of them has both the H coming out, whereas in other one both the H are going in. This one is called the endoadduct and this one is called the exoadduct. How do these names arise? These names will arise from the relationship in space between the carbonyl groups on the dienophile or electron withdrawing groups on the dienophile and the newly formed double bond in the middle of the old diene. If these are on the same side, then these are called endo. And if they are on opposite sides, they are called exo. Okay. So you can see here, this particular fellow can give you an exo product or can get an endo product. In the endo product, you have more steric hindrance, whereas in the exo product, you do not have that much steric hindrance. Therefore, the exoadduct is more stable energetically than the endoadduct. However, if you see from this particular example, the endoadduct forms very quickly and the exoadduct takes time to form or forms only at very high temperatures. Now, obviously, there is some kind of stabilization in the transition state which leads us to the endo product. This stabilization obviously is not available in the exo transition state. So you can see here one of them seems to be a product of kinetic control. The other one seems to be a product of thermodynamic control. So what is the Alder's endo rule? According to this rule, the dienophile approaches the diene preferentially in the endo mode. so as to allow the maximum spatial overlap of the unsaturated centers of the diene and the dienophile. Other than this, there is a overlap of the orbitals on the C1 and C4 positions of the diene with the orbitals of the dienophile. Therefore, the overlap is possible between the orbitals of the unsaturated functional group and the orbitals on the C2 and C3 of the diene unit only when an endo approach is possible. Okay, so you can see here in both these cases there is a secondary orbital overlap between the electron withdrawing group on the dienophile with the orbitals at the C2 and C4 positions of the diene. So you can see here very clearly from this particular diagram what kind of bonding interactions are there. So you can see here these are the orbitals, the frontier orbitals overlap. Okay, so these two portions are going to overlap with these two ends, whereas there is a secondary orbital interaction already developing between the orbitals on the C2 and C4 and the orbitals on the diene, and therefore this secondary orbital interaction favors the endo product. Let's see what happens in the intramolecular Diels Alder reaction. In the intramolecular Diels Alder reaction, very often what happens is, since they are already very close to each other, you don't need any activation. The barriers are rather low. The reaction proceeds very readily even without conforming to the cis rule or the endo rule. So you can see here in this particular example, you see what is dominating here is not the electronic effect but the steric effect. In this particular transformation, there is no activating group, but the reaction still happens. Why? Because this is intramolecular, as I had told you. There is no conjugating group on the dienophile, and therefore there are no orbitals to overlap with the back of the diene. So what does the molecule do? The molecule simply folds up sterically in the most favorable way, with the linking chain adopting a chair-like conformation, and this leads to a trans-ring junction. So you can see here this is the transition state conformation for the 4+2 cycloaddition. Obviously, you can see here now this is leading to the exo product. On the other hand, if you have this particular transformation, this very clearly gives you endo product. Why? Because now the molecule has to fold so that the carbonyl group can have a bonding with the rear of the diene or the back of the diene. For this, the chain, that is this, has to adopt a boat-like conformation. In the previous case, we had seen that the chain had adopted a chair-like conformation. So it's not necessary that the Diels Alder reaction may give you the endo product. Depending on the structure, you can have either of these two products, or you may have a mixture. What can Lewis acids do in Diels Alder reactions? Lewis acids are known to catalyze Diels Alder reactions. They coordinate to Lewis basic sites, which are usually the heteroatoms on the dienes. And these heteroatoms will bear a lone pair of electrons, and therefore, if this Lewis acid coordinates to those atoms, heteroatoms on the Diels Alder system, they behave as electron withdrawing groups. In being electron withdrawing groups, they lower the LUMO energy. Therefore, a Lewis acid coordinated dienophile will have a lower HOMO-LUMO energy, and therefore the gap between the HOMO of the diene and LUMO of the dienophile is reduced even further, and because of which the rate of reaction of a Lewis acid catalyzed Diels Alder reaction is increased. As you can see from this particular transformation, without any Lewis acid, if this mixture of two methyl vinyl ketone and the two substituted butadiene are reacted in a sealed tube at 120 degree. This is the mixture of products that is formed. However, with tin tetrachloride as the Lewis acid, this reaction proceeds beautifully to give you 93% of this particular isomer, whereas 7% of the other isomer. Similarly, you can see here in these examples, once again tin tetrachloride has been used in this particular transformation, which is very similar to the transformation that we are seeing on your left. On the other hand, this particular one gives you a measure of endo versus exo ratio when this is done with Lewis acid conditions. What about the Regio selectivity for Diels Alder reactions? Diels Alder reaction between an unsymmetrical diene and an unsymmetrical dienophile can lead to the formation of a mixture of regioisomers. What will this depend on? This will depend on the relative orientation of the diene and the dienophile in the transition state. The dienes which are substituted at the 1 position, okay, dienes which are substituted at the 1 position, that means these kind of dienes can give a mixture of 1,2 or 1,3 disubstituted cyclohexene in the Diels Alder reaction. That means you can get an ortho-like or a meta-like. If you have the substituent at the 2 position of the diene, you can get either a para-like, that is 1,4 like, or a meta-like, which is 1,3 like. Thankfully for us, the Diels Alder reaction is quite regioselective. Not only that, it is also quite stereospecific too. Therefore, normally it is observed that ortho and para adducts dominate over the meta adducts. So mostly you will get, depending on the substituents, either the ortho product or you will get the para product. You can see here from this particular table, for example, let us consider this one. This particular table, you can see here the regioselectivity becomes more and more high and better when you go towards the ideal situation. That means electron rich diene and electron poor dienophile. Why does this happen? Why does this ortho and para selectivity come? Suppose we consider butadiene, simple butadiene. This butadiene is symmetrical, and obviously the coefficient of the atomic orbitals on the HOMO and LUMO are exactly the same. So when the substituent is introduced at C1 or C2 positions, obviously the coefficients of the atomic orbitals in C1 and C4 will differ. For example, if you have a methoxy substituent on the C1 or C2, definitely the atomic orbital on C4 will be much different from butadiene. And if you have an electron donating substituent on the first position, then the coefficient usually on position number 4 is much larger than on C1. Similarly, for the dienophile, the substituent will also affect the coefficient of the atomic orbital on C1 and C2. As you can see here on this particular figure, so what you can see here are the relative sizes of the atomic orbitals in variety of dienes and dienophiles. Okay. The size here is roughly proportional to the magnitude of the coefficient. Okay. So if you see the one substituted diene, you see in the HOMO that we consider usually for electron-rich dienes, the coefficient is highest at this particular position when you have the substituents at this point. Okay. C could be conjugations. Z could be an electron withdrawing substituent. Okay. So you see here when Z is present, the coefficient is the smallest here. Whereas when X, that is electron donating substituent, is present, the coefficient here is the highest, followed by a conjugating group. Then the coefficient is slightly smaller but much bigger than Z. And like we mentioned earlier, when the coefficient is Z, that is electron withdrawing substituent on the diene, then the coefficient here at the C4 or C1 position, as you can put it, will be much smaller than the other two cases. Similarly, what happens to the LUMO? When you have the LUMO, you will consider the LUMO for the diene only when you do the inverse electron demand Diels Alder reaction. So you can see here when electron withdrawing group is present, the LUMO is the highest at the C1 position. Okay, so when you have electron withdrawing groups on the diene and electron rich on the dienophile, then you would have an ideal situation where the sizes of the orbitals would match. So we are seeing here the orbitals from the top. Okay, at this moment, do not bother about what is shaded and what is not shaded. Okay, what is more important for you to understand is why this particular orbital has a larger coefficient at this particular position, which obviously translates into a transition state like situation. So when two unsymmetrical p components interact during the course of the reaction, they will do so in two possible modes, as you can see here. So if the HOMO of the diene is considered and the LUMO of the dienophile is considered, so you can see here there is a large interaction. Whereas in the opposite case, in the meta case, you can see here there is a large small interaction, and here also there is a small large interaction. Okay, so you can see here a large or a small interaction will be far more effective than a large small or a small large interaction. Okay, so what is the outcome? So you can see here at the C2 position we have an electron donating group. So obviously you are getting the para product as the major with Lewis acids that coordinate with the carbonyl functionality, thereby increasing the electrophilicity and also increasing the coefficient of the LUMO for your dienophile. This gives you a much better overlap, and therefore this isomer is almost at 93% at 0 degrees Celsius. Okay. Similarly, when you have a methoxy group at this position, again the major product is the para product. On the dienophile possessing two methyl groups, you get the major product as the ortho product and the minor product as the meta product. So there is a bit of a bonding difference when these dienes and dienophiles are substituted. When this is highly electron rich, it is found that the bond formation is almost complete in the transition state at this particular point, whereas at this particular point the bond formation in the transition state is slightly slow, thereby leading to reactivity change in the Diels Alder reaction. The next example you can see here once again, this is electron rich and this is electron poor. Therefore, the Diels Alder reaction upon the transformation gives rise to a 1,4 disubstituted cyclohexene. Thus, we can remember this as a summary when C is electron withdrawing or a conjugating group, and in this particular case, if X is electron withdrawing, then you will get this particular Regio selectivity, the ortho selectivity as mentioned, whereas when you have electron donating substituents like alkyl, aryl, alkoxy, silyloxy or NH2R, then you will get the para adduct via a Diels Alder reaction provided Z is electron withdrawing. Alright, let us see a couple of examples of the Diels Alder reaction. Now, since 1928, the Diels Alder reaction has been used widely in organic synthesis. Why? Because you can predict the regio and stereoselectivity of the reaction very easily. And these days, Lewis acid catalysis has improved the efficiency in both regio and stereoselectivity of the Diels Alder reaction. Now you can widely vary the diene and dienophile in the transformation, and you can use this for the construction of a variety of complex carbocyclic and heterocyclic frameworks along with variety of functional groups. Also, the very fact that catalytic enantioselective Diels Alder reactions can be used in the enantioselective synthesis of complex natural products. Let's see a couple of examples. So you see here this particular dienophile has two portions. One is this alpha beta unsaturated system, the other is this alpha beta unsaturated system. This is a benzoquinone derivative, but you see here this is less electron rich than this. your diene is already electron rich. Okay, it is a normal type of diene with no electron withdrawing effects on it. Therefore, you get the reactivity arising only out of this particular enone system and not the electron rich enone system. So you get this particular transformation, and you can note here that this is also an endoselectivity. Similarly here in the second case, here also you are getting an endoselectivity. So you get this particular substrate after this selectivity, and after several steps this can be converted to reserpine. In the lowermost example you see here, both of these components are quite electron rich. Nonetheless, attempt was made to synthesize the cycloadduct. The yield was not all that great, only 37%. You can see in the previous case also, the diene and dienophile are both electron deficient, because of which you get a rather poor yield of 27%. This particular adduct is then taken forward, it is hydrolyzed to give you this tetrahydroxy derivative. This can once again be treated with a variety of reagents to give you inositols. Now, ketenes do not react very well in Diels Alder reactions with dienes. But if if the dienophiles, for example chloroacrylonitrile or nitroethylene, are used, these will undergo a Diels Alder cycloaddition, and they can be used as ketene equivalents. For example, let's see these particular transformations. After functional group interconversion, the cycloadduct can be used to give you a ketone derivative. So you see these three examples. Here the cycloadduct is formed with this particular substitution pattern. Similarly here, and at this position it is CNO2. And you see here, after basic hydrolysis, in both the cases, this is removed very easily, does not affect any of the previously formed stereocenters, and gives you this equivalent product of a ketene cycloaddition. So this is an indirect method of making cycloadducts which could have arisen from ketene. In this particular example, you see here what we are seeing. We are seeing first an electrocyclization to give you this particular diene. This then reacts with diphenyl sulfone alpha beta unsaturated one, which then gives you a 4+2 cycloaddition in a regio and stereospecific fashion. This is then treated with tungsten dichloride and N-butyl lithium. N-butyl lithium converts the tungsten hexachloride to a very low valent tungsten compound, which then effectively carry out the deoxygenation reaction to give you this particular cycloadduct. This is then very easily removed. The sulfone groups are easily removed using a reductive cleavage of these cycloadducts. Now, benzene is a very reactive dienophile and can react with poorly reactive dienes systems. So you can see here it reacts with furan to give you this particular cycloadduct, whereas it reacts with anthracene at the 9 and 10 position, as this is more or less like the central ring is more or less like a in isolated uh, non-aromatic system, therefore giving you a diene-like property, and this leads to a very efficient 4+2 cycloaddition. In this particular transformation, we had seen the synthesis of buscatine earlier. Buscatine is synthesized starting from cyclooctatetraene. This undergoes an electrocyclic ring closure to give you this diene system, which then undergoes a 4+2 cycloaddition to give you this cycloadduct. This cycloadduct is then treated in a 2+2 supra-antra overlap, and gives you this buscatine skeleton, which is now treated with lead tetraacetate, and oxidatively the cleavage of this anhydride system to give you buscatine in a very efficient manner. This is the skeleton of the compound pagodine. This can be synthesized by a double Diels Alder reaction. You see here the first Diels Alder reaction gives this particular cycloadduct. This now undergoes another Diels Alder reaction at this position to give you this second cycloadduct. This second cycloadduct can be transformed into pagodine by simple transformations. The second one is another example of a multiple Diels Alder reaction. So in this case, you can have either the endoadduct or the exoadduct with respect to this particular tether. Accordingly, you can have another 4+2 cycloaddition giving you either this or this product. Similarly, two furan molecules will react with diethyl acetylene dicarboxylate to give two Diels Alder adducts, therefore generating this highly substituted cage type structure. There's another concept called as the retro Diels Alder reaction. The retro Diels Alder reaction is very important, especially when it comes to the cracking of cyclopentadiene. Cyclopentadiene is highly reactive and even at room temperature undergoes dimerization via a 4+2 cycloaddition with another of its own partner. When you heat this at very high temperature, greater than 150 degrees, then a process of cracking takes place, thereby converting cyclopentadiene dimer to cyclopentadiene. This has then to be used very quickly before it starts to dimerize. Now this retro Diels Alder reaction takes place in this particular way. Similarly, you can see here in the second reaction, first Diels Alder transformation gives you this bicyclic structure. This bicyclic structure then undergoes a retro Diels Alder reaction to eliminate a benzonitrile portion, thereby generating a new furan system. This is very useful in very lots of natural product synthesis. Similarly, this particular so-called aromatic system, this trizene, can undergo a Diels Alder reaction with this particular dienophile to give you this pyridine system. However, this pyridine system actually arises from this cycloadduct, the first cycloadduct. This cycloadduct can lose a molecule of nitrogen and it can lose a pyrrolidine, thereby giving you this pyridine system. Let's see some examples of an intramolecular Diels Alder reaction. You can see in this first particular case, this undergoes a beautiful intramolecular cycloaddition over a period of 3 days to give you this particular endo adduct. This is then treated with methanol to cleave this silyloxy group. It gets converted to a ketone to give you this tricyclic molecule. In the synthesis of chelidonine, this particular substrate underwent an electrocyclic ring opening to give you this orthoquinodiamethane. This then underwent an Diels Alder reaction with the acetylene, which is there in the proximity, to give you this polycyclic molecule, which under several transformations then gives the natural product chelidonine. You see in the third example, this diene system reacts with the indole olefin under reflux conditions, giving you this strychnine skeleton. Strychnine is an alkaloid which proceeds via this particular intermediate. In this intermediate, you then have the extrusion of nitrogen gas, thereby giving you this highly important strychnine type of skeleton. These are another examples of intramolecular Diels Alder reactions. So in the first reaction, you can see here, this gives a mixture of products arising from the endo and exo. This is a beautiful example of how Diels Alder reaction can be used in an intramolecular fashion. In this particular case, the dienophile is generated in this way by heating. It leads to a loss of acetic acid, thereby generating a highly reactive species. This species undergoes a 4+2 cycloaddition to give you this fused ring system. In the third case, you can see here, this is a free amine. Reacts with formaldehyde, gives you this imine type of system. This imine immediately reacts with a dienophile, with a diene, gives you this mixture of isomers. As I had mentioned earlier, the Diels Alder reactions allow the formation of up to 4 contiguous asymmetric centers. So if we consider the reaction between an unsymmetrical diene and an unsymmetrical dienophile, if the reaction is orthoselective, then a pair of diastereomeric products can be expected, depending on whether it is an endo or exo approach of the diene and the dienophile. Most of the Diels Alder reactions will proceed with very high endoselectivity. Therefore, the only thing that we need to then consider is a pair of enantiomers or diastereomers. If you see here in this particular in this particular diagram, you will have either an approach from this particular phase or this particular phase. Okay. Now, in the approach from phase A, you would get one particular isomer, whereas from approach from phase B, you would get another isomer. As you can see, with respect to the plane of the diene, the adduct that rises from the two approaches usually are related by mirror symmetry, and therefore they are enantiomers. So you can see here, these two are enantiomers. both arising from the endo approach. Whereas these two are enantiomers, both arising from the exo approach. So that's what you need to control when you're doing an asymmetric Diels Alder reaction. In the asymmetric Diels Alder reaction, earlier optically pure dienes and dienophiles were used. Then came the use of the removable chiral auxiliary based reactions. That means you could use a chiral auxiliary somewhere either on the diene or the dienophile, and those could be removed at a later stage. We'll see examples of these. Then came the use of stoichiometric chiral Lewis acids, and we saw how Lewis acids can be used in the Diels Alder reaction. And then presently there has been a huge explosion in the use of chiral Lewis acids as catalysts in Diels Alder reactions. Let's see some of these examples. So you see here, this is an example where an auxiliary type moiety is used on the diene, and this can now be hydrolyzed to get rid of the chiral auxiliary, thereby giving you an enantiomerically pure material. This reaction is catalyzed by boron triacetate or the anhydride of boric acid. This diene is called the Daniszewski diene. This Daniszewski diene, it reacts in a hetero-Diels Alder reaction with this particular compound, thereby giving you a beta pyrone kind of system in very high enantioselectivity. This is catalyzed by a box ligand. This is called as a bis-oxazoline ligand, which is a chiral catalyst with copper chelated in between. So one can use transition metal based catalysts with chiral ligands, and these give rise to very good selectivities in the Diels Alder reaction. In the next example, you can see here, this is an aluminum based system. This is a C2 symmetric ligand. This particular catalyst has been used in 10 mole% for this Diels Alder reaction. This is a highly reactive cyclopentadiene derivative, thereby leading to beautiful synthesis of a chiral bicyclic system. In the next example, you can see once again, this is also an oxazoline based ligand, chiral ligand. Again, it is copper based. This also is the synthesis of a bicyclic compound and has been carried out at low temperature with very high selectivity for the exo. You have 97% selectivity for the exo, depending on what group has been used for this particular transformation. The enantiomeric excess is very high. Very appreciable enantiomeric excess has been obtained with this particular ligand. Okay, so today we saw a lot of transformations based on the Diels Alder reaction. Moving further, we will then see in the next class dipolar cycloadditions. Thank you, everybody. We'll see you at the class on Monday. Goodbye.